So for the double slit experiment, the usual setup is we've got a wall or some sort of barrier with a couple of gaps in it. And you've got some source, usually a light source. And this doesn't have to be light. This could work with any sort of wave. But let's assume light for now. So the light is shining out of this. And what happens to the light when it hits this wall?
It gets diffracted.
Sorry, what was that?
Does it get diffracted?
Yeah, at these slits, at the holes, it gets diffracted in the sense that it's spreading out from those slits. The wall itself blocks the light from getting through. The light can only get through at these slits. And each of those slits essentially acts like a new source. Then instead of the light just, if in general, if you've got a barrier with a gap, and you've got light or whatever wave coming along like this, you might expect the light to just come through like this, like everything else gets blocked. But what actually happens is that the light acts like it's spreading out from that point as a new point source. So it's not just continuing in a straight line from there, it's spreading out spherically from there as if that were the source of the light. So the light's going to be traveling from each of those slits outwards in all directions. And we could draw out wavefront diagrams. We could draw out the wave spreading out from that source and the same wave spreading out from this source, and then start looking at the overlaps. If we want to look for everywhere we get crest and crest overlapping, or trough and trough overlapping, and we're going to end up with this pattern of constructive interference zones and destructive interference zones. But the wavefront diagram quickly gets very cluttered and difficult to interpret. So instead of looking at the wavefronts, we're generally going to look at this as a ray tracing diagram. Instead of looking at the entire wave, we're just going to focus on the path the waves take to get to a specific location. To start with, let's say we're taking a look at the location straight across from right between the two slits. And we're typically going to be describing this based on angle of elevation. So we're going to call this location theta equals 0. And then all the other locations on the wall, we're going to label as some sort of angle. Like this location, we label based on this angle theta. If we're talking about the points directly across, though, what would you assume about this path from this slit to the point of interest directly across, and this path? What would be your assumption about those two paths?
Path length is 0.
Yeah, or I would say difference in path length is 0.
Oh.
Delta x equals 0. There is certainly a path length, but there's no difference in that path length. They're traveling the same distance because of the symmetry of the geometry here. So there's no difference in path length. And of course, there's no difference in frequency because these are really coming from the same source. And also because they're coming from the same source, we can assume no phase difference either. So that means there's no difference at all between the waves. It's the same wave traveling the same distance. So what type of interference would you expect?
Constructive interference?
Yeah, this would be constructive interference because there is no difference. And so we're going to see a bright spot here. This is going to be a bright spot, usually called the central maximum. Central in the sense that it's in the center of the pattern, and maximum in the sense that it's maximum brightness. So that's the central maximum of the pattern of light we're going to see. If you look at another location, we have to consider differences in path length, because any other location other than the exact center, let's say we're talking about this location here. And again, we're going to label it not so much with a distance, but with an angle. angle of elevation theta. If you actually draw out the paths here from this source, that is this slit in the wall, to this location, versus the other path from this source to this location, those waves, are they still traveling the same distance? No. So we are going to have a delta x. We're going to have a difference in path length. If we call these, let's say, x1 and x2, there is a difference in path length. Let's say we call that, it looks like x2 is longer, so let's just calculate x2 minus x1. And to figure out that difference, geometrically, we could just think of it as like take distance x1 and swivel it and cut that distance off from x2 so we can see what's left. If you swivel this around, like just imagine taking x1 and rotating it and cut it off. This distance is x1. If we deduct that from x2, then whatever is left here is the delta x. That's the extra distance traveled. If there's any interference at all, the type of interference is caused by this extra distance. Everything beyond that, like if you imagine back tracing from the destination, same distance except for this extra bit of distance. So this extra bit of distance here is what we really care about. Any questions on that so far?
Can you explain why it has to be perpendicular?
What has to be perpendicular?
Where I guess the delta x would be from path length x1 versus.
Oh, like this distance versus this?
Yeah, exactly what you were just pointing to.
Generally speaking, this would not be a straight line. This would be the curve of a circle, because we're basically taking this x1 and rotating it. So the path taken by the endpoint, if you rotate that line segment, would be the circumference or an arc of a circle, a portion of the circumference of the circle. But if you take a circle and look at a radius and another radius, the arc of the circle is going to be perpendicular to any radius. So formally speaking, this is actually not a straight line. This is the arc. This is an arc of a circle, which is perpendicular to both radii. But since we're talking about a very small arc of a circle, we're generally assuming the slits are very close together compared to the other distances. So since it's a very small arc of a circle, we can treat it as being almost like a straight line. Or if you think of it as a triangle, if you got a very long side here and a very long side here, formally speaking, these can't both be 90 degrees because the angles have to add up to 180. You can't have 90 plus 90 plus, then there's nothing left over here. But if this angle is so small that it almost rounds off to 0, then these two angles would both be almost 90 degrees. And we're going to approximate here. We're going to round them off to 90 degrees, even though they're both more like 89.9 something. But the mathematics works out just fine. We're just looking for a close enough approximation anyway. So we can assume that this angle and this angle are both close enough to 90 degrees. Any other questions on that so far? And if we need to figure out what's that distance, because that distance is really what causes what type of interference we get, then we're going to need to zoom in on the geometry there. If we take a close look at this triangle here, so we've got a path, we've got the wall. So this is just the distance between slits, which we usually call lowercase d. So our lowercase d here is the distance between the slits, which we are generally going to assume is a very, very small distance. And then we drop in this perpendicular here. And this distance is the delta x we actually care about. So to find that delta x, what other information are we going to need?
Theta?
Yeah, we're going to need theta, the angle. And formally, theta is the angle between either of these and the horizontal. So let's say we mark this angle as theta. But we're assuming that the ray of light and this dotted line here form a right angle. So if this is theta and these form a right angle, what does this angle have to be?
-90 minus theta.
Right, these have to add up to 90, so this one has to be 90 minus theta. But also, this is a right angle, the angle between the wall and the horizontal. So that means this angle plus this angle adds up to 90. So what would this angle have to be to make these add up to 90?
Theta.
Yeah, this ends up just being another copy of theta. So the triangle we've got here, this triangle we really care about, has an angle of theta in this top narrow quadrant here, or this top narrow corner. And if we now have d theta and a right angle, how can we express the relationship between delta x and the distance between slits in terms of this angle theta? What trigonometric function would work there? Yeah, sine theta will work perfectly because delta x is opposite to the angle and d is the hypotenuse. Opposite over hypotenuse is sine. So we can clearly say that sine theta has to equal opposite over hypotenuse. That's delta x over d. And then if we just multiply both sides by d, we'll have delta x. Delta x equals distance between slits times sine of the angle of elevation. So that's a very useful formula for delta x in this scenario. In this particular situation, the extra distance traveled by one of the rays of light is going to equal the distance between slits times the sine of the angle of elevation. Any questions on that so far? So we get that from geometry alone. In this situation, geometry says delta x equals d times sine theta. But what we really care about is what type of interference that leads to. Let's say we're specifically looking for bright spots, like the essential maximum here. If we take a look at interference in general, keep in mind we're assuming that the only difference between these paths is their delta x. They have a path length difference, everything else is the same. In that case, so in general, if delta x is the only difference, so same frequency, same phase shift, same everything, the only difference is they're traveling different distances. When would you expect constructive interference? What has to be true about that difference in path length?
Delta x is a multiple of a wavelength.
Yeah, it's got to be a whole number multiple of the wavelength. Let's say n times lambda. Because if it's not a whole number multiple of wavelengths, the waves are not offset by a whole number of cycles. So we've got to assume, if we're specifically looking for constructive interference, a bright spot, we have to assume that delta x equals a whole number of wavelengths. And we can now combine this information. We can combine the delta x we got from the geometry of this situation with the delta x we should expect if we're looking for constructive interference in general. So we can just set those equal to each other. And this suggests we get constructive interference, double slit, constructive interference occurs when this formula equals this formula. D sine theta equals n times lambda. And this essentially gives us a recipe for what angles will work. If you know the distance between slits and you know the wavelength of the light, you can plug in any whole number you want for n and calculate what theta is going to be. That tells you an angle, a theta value that will cause a bright spot at that location. And it's useful to think of n here as basically keeping count of which bright spot you're looking at. The central maximum is going to be n equals 0. The very next bright spot beyond that will be n equals 1. The next bright spot is n equals 2, then n equals 3, and so on. And you can treat the bright spots below the center as having like n equals -1, n equals -2, and so on. So that tells you where to find bright spots. And what you know versus what you're trying to find varies depending on the situation. One common use of this is if you're dealing with a situation where you don't know the distance between slits, usually because that distance is so small that there's no way you could measure it with a ruler. So let's say you don't know the distance between slits, but you have a laser that provides a very specific wavelength that you know. So you know the wavelength, you don't know the distance. Could you measure theta? If you have this set up in a laboratory setting, could you measure the angle? We have tools for measuring angles, right? A protractor, or even if you don't have a protractor, you could measure how far it is along the horizontal, and you could measure how high up the bright spot is, and then use inverse tangent to find the angle. So you can certainly find the angle if you know where a bright spot is. Like let's say you find maybe the fourth bright spot. Maybe the first 3 bright spots are so close together you can't really measure them very accurately. But you measure the location of the fourth bright spot and you figure out what that angle is. You could plug in 4 for n, the angle you measured for theta, the wavelength of the laser you're using for lambda, and then what's the only unknown left? Yeah, d is the only unknown left. So you could solve for distance d, the distance between the slits, and that tells you how far apart these slits are. Even if they're way too close to be measured by a conventional ruler, by shining light on it, measuring the locations of the bright and dark spots, and doing a few calculations, you can determine what the distance between slits is going to be. And this allows you to be very, very precise about it, even if it's an extremely small distance. Or alternatively, maybe you've already determined the distance between slits, and now you shine a different laser onto it and you don't know the wavelength. If you know the distance between slits, and you can measure the angular location of some bright spot, and count which bright spot it is as measured from the center, you can then solve for lambda and figure out what's the wavelength of this new laser. So as in any situation with 4 variables, as long as you can measure 3 of them, you can immediately calculate the 4th one. Any other questions on that so far?
I have a quick question. I'm not sure if this is right, but I was reading about the double slit experiment online, and they said that the central maxima is the brightest out of all of the bright spots. Is that true?
Yeah. And that's largely just because both of the waves are traveling a short distance. If you look at the other bright spots, the waves have to travel further. And due to dissipation, is that right word? Diffusion? Or the fact that they're traveling further means that the energy is getting more and more spread out. So the further light travels, the weaker it gets, because it's becoming, not because it's losing energy, but because the energy it carries is becoming more and more spread out. So the spots further away are going to look dimmer, largely because the waves are traveling further, and therefore the energy gets more spread out. But the energy is going to be most concentrated at the center, so that's going to be slightly brighter than the other ones. But all of these bright spots still count as constructive interference. Meanwhile, if you wanted destructive interference, what would we assume instead of this?
Would it be 2n plus 1 wavelength times wavelength?
2n plus 1 is still a whole number. And any whole number of wavelengths is going to be constructive. But yeah, n plus a half, if you have something and a half wavelengths. So like these bright spots represent 0 wavelengths offset, 1 wavelength offset, 2 wavelengths offset, 3 wavelengths offset, and so on. If you look at points in between those, you're going to get a dark spot where it's half a wavelength offset, another dark spot where it's 1.5 wavelengths offset, another dark spot where it's 2.5 wavelengths offset. So to find the dark spots, instead of using n times lambda, you could use n.5 times lambda. Still largely the same formula, you just have n.5 times lambda. Or alternatively, you could use the same formula for both. Just use whole numbers for n when you're talking about bright spots, and use something and a half for n when you're talking about dark spots.
I had a quick question. Did you say that the going from one bright spot to the next, is that representative of one wavelength difference?
I mean, the distance itself is not one wavelength, but the difference from here to here represents, at this point, like at the very center, the waves are traveling the same distance. At the next bright spot, the waves are traveling different distances, and the extra distance traveled by one of them is 1 extra wavelength. And then the next one, they're traveling different distances, and the longer wave is traveling 2 extra wavelengths. The next one, the longer path is traveling 3 extra wavelengths, and so on. So the n value is basically how many extra wavelengths the longer path is taking. And yes, the dark spots would be destructive interference. So you end up with this alternating pattern of bright, dark, bright, dark, bright, dark, bright, dark, and also same thing below, bright, dark, bright, dark, bright, dark, because of alternating constructive interference and destructive interference. And each angle, by using this equation, you can determine if any angle you want is constructive, if n is a whole number, destructive if you have something and a half instead of a whole number, or partial would be anything in between those, anything that's not a whole number or something and a half. Any other questions on that so far? And one other useful bit of algebra and geometry here, sometimes measuring the angle isn't very convenient. You wouldn't want to have to put up a protractor in the middle of the screen or something. It's usually a lot easier to measure distances. You just put a ruler here and measure how many centimeters or whatever each bright spot is from the center. So if we rework this in terms of distances instead, let me tighten this up a bit. Let's say we're looking at this bright spot. And let's say we call this distance y. And let's call this distance, I think this distance is usually called capital D. The distance, the horizontal distance from the slits to the other wall, the screen or whatever, where the pattern is being broadcast. Then to figure out the relationship between those, we're still using theta to represent the angle of elevation here. How would y, the vertical distance, and big D, the horizontal distance, be related to theta here? What trigonometric function would work there?
Root tan.
Yeah, tangent works fine here. Because tangent is opposite over adjacent. Opposite is y, adjacent is d. So the tangent of the angle is y over d. Problem is our formula doesn't have tangent, our formula has sine in it. But the thing is we can use what's called the small angle approximation. If theta is very small, if we're talking about a very flat angle here, sine theta isn't opposite over adjacent. Sine theta is what?
Opposite over hypotenuse.
Right. Opposite is still y. Hypotenuse would be this diagonal distance here. Let's say capital H. And so those are not quite the same thing. Y over d and y over h are not going to be the same. But if the angle is small enough, what would we assume about the distance h and the distance d? They're the same. Not exactly the same, but pretty close to the same, close enough. So if theta is very small, we can say that sine of theta and tangent of theta are almost the same. You can even see this on a graph. If you make a graph of tangent theta and a graph of sine theta, sine theta is our usual wave function. Whereas tangent theta looks more like this. So they're very different graphs, but if you look very close to 0, for small values of theta, sine theta and tangent theta are almost the same graph. So we can assume that as long as theta isn't too big, as long as we're dealing with small angles, we can assume that sine theta and tangent theta are almost the same. And this is usually called the small angle approximation. Another convenient approximation you can often use is that as long as you're using radian measure, sine theta is approximately equal to tangent theta is approximately equal to theta itself. Because if you just graph y equals theta, you get a straight line through the origin. But as long as you're using radian measure for the angle, that straight line is pretty close to the graphs of sine theta and tangent theta if you're close to the origin. So as long as theta is small, sine theta, tangent theta, and theta in radian measure are all pretty close to the same value, and you can make those substitutions to make the calculations easier. In this case, if we make that approximation, we can say d times tangent of theta is approximately n lambda, again, for bright spots, constructive interference. And we know tangent theta can be rewritten as y over d, specifically y over big D, y being the vertical height from the central bright spot to the other bright spot we're considering, and big D being the distance from the slits to the wall. And the nice thing about this formula is it's now entirely in terms of distances. This formula no longer has to care about angles. It's just distance between slits times height of the bright spot we care about divided by the long distance from the slits to the wall is approximately equal to number, which bright spot we're talking about, a whole number, times the wavelength. So that's a very useful comparison involving just distances, not having to worry about angles at all. And of course, it's only valid if theta is pretty small, if you're talking about spots close to the center. But for those spots, it's a very convenient measurement. Any questions on that so far?
Do you mind like going over what is valid for like a small theta?
I mean, it kind of depends on how much accuracy you want. I would just say if you're talking about close to the center, maybe, I don't know, I don't really want to put an exact value on it, but maybe less than 5 degrees or something like that I would expect that in an actual applied problem here, it would specify use the small angle approximation or assume that the angles are very small or something like that. But in practice, like in an actual real world scenario, it would depend on how much accuracy you actually care about. Any other questions on that so far?
I was wondering why the upper dotted line makes a right angle with y. Is it because that's a small angle?
This one actually isn't a right angle. It's gonna be, I mean, this is a right angle.
Oh, gotcha.
This one's going to be 90 minus theta. But
Okay.
again, we're assuming theta is very small. So 90 minus theta will be pretty close to 90 degrees. It's not
Gotcha.
truly 90 degrees, but it's close enough. We can often round it off to it.
Thank you.
Any other questions on that? One of the other neat aspects of this is if we actually solve this for y, just by multiplying by capital D, the horizontal distance, and dividing by little d, the distance between slits, we're going to get n times lambda times big D divided by y times little d. Wait, I missed that. I'm leaving y over there. And this is just a constant. So that means the y values, the heights of the bright spots, are going to be a constant times a whole number. If this is just some distance, we get 1 times this distance, 2 times this distance, 3 times this distance, 4 times this distance. So we're going to have some distance above the center to get to the first bright spot, then twice that far to get to the next bright spot, 3 times that far to get to the next bright spot. This tells us the bright spots are going to be evenly spaced, assuming we're close to the center and can use the small angle approximation. When you get further from the center, it's not really evenly spaced anymore. But if you're close enough to the center that you can use the small angle approximation, the bright spots are going to be pretty close to evenly spaced. And note that the distance between them depends on the distances involved, but also depends on the wavelength. So if you switch to a different wavelength of light, the bright spots are going to get more spread out or less spread out, depending on whether you're increasing or decreasing the wavelength. And what does wavelength of light really represent? What would you see if two beams of light had different wavelengths?
Different colors.
Yeah, different colors. So if you use a certain color of light, you're going to get bright and dark spots spread out a certain amount. If you switch to a different color, you're going to get a similar looking pattern, but maybe more spread out or maybe less spread out, depending on whether you're looking at a longer wavelength or shorter wavelength. So different colors are going to lead to different spread outness, different compactness of the pattern. Same pattern, just more or less spread out for different colors. Any other questions on all this double slit stuff? All right, then let's take a look at beats, which is another phenomenon involving interference. And beats is kind of an unusual situation because in all the interference stuff we've been seeing so far, we're assuming the waves are basically coming from the same source or equivalent sources, but they're traveling different distances. Beats is a situation where we don't really care much about distance, but what is happening that causes beats to happen? Why would you hear beats if you're listening to two sounds? What would have to be different? Yeah, they got to have different frequencies. Beats is something that occurs if you're listening to two sounds that have different frequencies. Yeah, they have to be pretty close together. If they're very different frequencies, your brain just interprets that as two different sounds. But if you're listening to two sounds that are almost the same frequency, but not quite, your brain sort of interprets that as, well, it's the same sound, but I'm hearing this weird sort of wobbling. And this is most noticeable if you're listening to two musical instruments that aren't quite in tune with each other. They're both trying to play the same note, but they're not quite in tune. In that case, what you hear is this weird sort of wobbling noise. Like it seems to be alternating between loud and quiet, usually many times per second. So it's just this weird oscillating wow, 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 wow sort of noise. So what causes that is alternating interference. Because if we have two sounds that are not quite the same frequency, if we've got, let's say, one musical instrument that's got a frequency of, let's say, F1 equals 400 hertz. And another sound, another musical instrument that's producing a frequency of F2 equals, let's say, 406 hertz. And you're standing in the middle in between, listening to this horrible sound, probably covering your ears because it sounds so awful. Then you're going to hear this as, you're going to perceive this as one unified sound, but with this really weird phenomenon of beats. Beat being the cycle of loud to quiet to loud. And what's happening here, if we actually draw out a phase chart to analyze the interference, we're going to have our 2 pi, instead of dividing by period, I'm going to write this as times frequency. I think that's going to make things easier. We're going to have our minus 2 pi x over lambda. We're going to have our plus phase shift equals total phase. Of course, we don't really care about the total phase. We care about the difference in total phase, comparing the two waves. So if we take a look at a difference in total phase here, is there any difference in this term? Yeah, the frequencies are different. The times are the same. Both of the waves are reaching your ears at the same time. So we can treat time as a constant as far as the delta is concerned. But the frequencies are different, which means this term actually matters. In all the other situations we've looked at so far, this term goes away when you take delta because there's no difference between the frequencies. But in this case, we apply a delta, 2 pi and t can be factored out of the delta because they're both arriving at the same time. So we get 2 pi t times difference in frequencies. And then here, the waves might be traveling different distances and they have different wavelengths. So we're going to have to write this as minus 2 pi times delta x over lambda. And they might have different phase shifts also because they're coming from different sources. So the difference in total phase comes from all of these terms together. All these together is what's going to cause the type of interference. But there's one very important variable that shows up in this that didn't show up in the previous interference examples at all. What new variable are we looking at here that didn't show up in all the other ones?
Is it period?
There is a difference in frequency, but that's just a number minus a number. We know what that number is. That's just going to be 6 hertz in this case. But the fact that that doesn't go to 0 means this term exists. And that term has what important variable in it?
Time.
Yes, this is now dependent on time. And this is really the biggest part, the most important part of this entire expression. All the other types of interference we had so far, when you calculate delta total phase, you just get some value that doesn't change as time passes, which means you calculate the type of interference and it just stays that type of interference forever if you're staying in that same place. But here you're standing in one place, so these terms don't change, but there's a term that has time in it, which means the type of interference changes as time passes, even if you're standing still. And because of that, because time is involved here, we're going to refocus everything on time. All this stuff, since it doesn't depend on time, we can treat it as a constant. Let's just call that, let's say, capital C. All this stuff is just some constant. It doesn't depend on what time it is at all. So then we have delta total phase equals 2 pi t times difference in frequency plus this constant. The constant doesn't really matter much. The important thing is that delta phi cycles as time passes. Because as we keep increasing time, this whole thing keeps increasing. And since we're talking about radians, we've got some starting value. We keep adding to it. Eventually we get back to the starting value, and we keep going around this cycle over and over again because we're talking about radian measure. And how much radians does it take to make one full cycle?
Two pi.
Right, 2 pi. So ignoring this c, because c doesn't really change here, if we just take a look at the portion that is changing, every time this portion increases by 2 pi, then we've gone through one full cycle. We've changed interference through one full cycle. We've gone from constructive to destructive to constructive, or from destructive to constructive back to destructive again. We've completed one beat, one full cycle from loud to quiet to loud. And so if we set this alone equal to 2 pi, and the time we're talking about here is really an interval of time, the time for one complete cycle. And what do we call the amount of time for one complete cycle? Yeah, that's the period. So I'm going to replace t here with capital T, the period. But note that this is not the period of the sound itself. The period of the sound tells you what note it is. This capital T here is what's called the beat period, which is how many seconds it takes, how long it takes from beat to beat, from loud to quiet to loud again. So that's called the beat period, the amount of time it takes from loud to loud. And if you solve for that, the 2 pi's cancel out. We just get beat period is 1 over the difference in frequency between the two different waves. Or alternatively, we could just invert both sides. What do we call the inverse of period? Right, the frequency. So we can say the beat frequency, meaning the number of loud to loud cycles per second, is the inverse of this. So that's just delta frequency. So the difference between these two frequencies tells you how frequently beats occur. And what is the difference between those? Yeah, they're different by 6 hertz. So that means if you're standing here listening, you're going to hear this horrible sound that's wobbling between loud and quiet and loud and quiet and loud and quiet 6 times per second. Any questions on that beat frequency so far? There's also another term called carrier frequency. Have you seen that term before? So what does that mean? What is carrier frequency? Yeah, that's the actual pitch you hear. Like I said earlier, when you're listening to these sounds that are pretty close to each other in frequency but not the same, your brain tries to resolve this as if you were hearing just one note. That one note is what's called the carrier frequency. That's the note of the sound you actually hear, the frequency you actually hear. And it turns out that's just the average of the two frequencies, which you would, as usual, calculate by adding them together and dividing by 2. Or you could just examine the numbers and ask yourself what's halfway between. So in this case, what is halfway between those? Yeah, 403. Yeah, go ahead.
Oh, sorry, that was an accident.
Sorry, what was that?
That was an accident, sorry.
Oh, okay. So what we would say here is that what you're hearing is a 403 hertz note halfway between the notes they're trying to play. And you're going to hear it wobbling between loud and quiet 6 times per second. And this is really what tells you these instruments are out of tune. Out of tune instruments sound bad because you're hearing this wobbling loud, quiet sound. And so to fix that, you would presumably have, let's say this one knows that it's the instrument's in tune, but this one is out of tune. They're supposed to be, let's say, at 400 hertz. So let's say this one tunes and makes it a little more in tune. Let's say 404 hertz. Now what's the beat frequency going to be? Yeah, beat frequency would be 4 hertz. There are now fewer beats per second. So if the beat frequency gets smaller, if you're going from lots of beats per second to only a few beats per second, if the beats seem to have slowed down, that means you're going the correct direction. You are getting closer to in tune with each other. And if they get really close, like let's say this is maybe 400.1 hertz. That's only offset by a tenth of a hertz. So you're only going to hear one cycle every 10 seconds. That's not even going to be enough to notice. So at that point, you say they're close enough to in tune. But if you are instead going the wrong way, like let's say you try to tune, but you accidentally pull the mouthpiece out when you should have pushed it in. In that case, if you're getting more out of tune, what would you notice about the beat frequency?
It would be higher.
Yeah, you'd have a higher beat frequency. You'd be hearing more beats per second. So this is a very useful way of being able to tell audibly, without even needing electronic equipment, if you're going the correct direction when you're tuning an instrument. If you're trying to tune an instrument to be in tune with another instrument, you have both instruments try to play the same note at once. If you hear beats, if you hear this wobbling loud, quiet, you adjust one of the instruments. If you now hear fewer beats per second, if they're more spread out in time, that means you're going in the correct direction and keep going. If you hear more beats per second, if they seem to be coming in faster and faster, you're going the wrong direction and you should be tuning in the other direction. So this is very useful as an intuitive way to tune instruments without needing any equipment. Any other questions on that?
I have a quick question on how this all relates to the Doppler equation, because my TA said something that I found very interesting. He told me I was confusing. Like, let's say you had like these two trumpeters playing two frequencies. You can say that the F carrier is equal to the F observed, right?
Well, the thing is here, we're assuming the listener is standing still and the musical instruments are standing still. So this situation, as shown here, has nothing to do with the Doppler effect. But some of the people who write physics problems really like combining them by saying, well, what happens if you run towards one of them? Because in that case, you're going to hear a different observed frequency. And if you run in the correct direction at exactly the correct speed, then it's going to sound like they're playing the same note, at which point you would get no beats at all. So if you want to move in a way that causes you to not hear beats, what I would do is write out an expression for the F observed that you hear from one of the trumpets and the F observed that you hear from the other trumpet, set them equal to each other, and figure out what speed you'd have to be going to make that happen.
So if you were the observer, you would want to run towards the trumpeter with the smaller frequency?
Yes, because if you're running towards the source, you're going to hear a higher frequency. And if you're running away from the other source, you're going to hear a lower frequency. And you want to be setting it up in such a way that you hear the same pitch from each one, even though they're producing different pitches.
And you can set the two Doppler equations equal to each other because you know that the F observed is going to be the same for both of them?
Or at least that's our goal. We want F observed from the first one to be the same as F observed from the second one. So I would write out a formula for F observed that you hear from the first trumpet and F observed that you hear from the second trumpet, and set those equal to each other because we want them to sound the same so that we don't get any beats at all.
Okay, thank you.
And I think at that point, the speed you're running, the speed of the observer would be the only unknown. So you can solve that for V observer. All right, that's all the time we have for today. But next time we will take a look into standing waves and more of the physics of how musical instruments work. Feel free to email me if you have any other questions, and I will see you then.
Thank you.
You're welcome.